Okay, I'm not going to wait for too long for this. I'm getting the document camera so I can get all the devices recorded. So this is the very last project we're going to work on for this semester. And I think, have you finished everything for this one? Or still working on it? Yeah. Okay. So what I'm thinking is probably I can make part 2 optional. We're running out of time. This is a shorter semester compared to others. So part 2 will be optional. So part 2 is mainly just the PCB design. It's actually a very good project. Just unfortunately, we don't have the time to get everything done. So in the past, we fabricated a little PCB out of this project and solder the ESP32 chip on the PCB, and plus the accelerometer and the voltage regulator. You can see that's a very special voltage regulator. Tiny. It's very difficult to solder. You have to change the grade to make it small enough in order to make a footprint out of it. And that's the regulator. And let's see what's the outcome here. So that's a PCB board eventually. As the regulator is tiny, it's the most difficult chip I have ever soldered in my life. And this is the accelerometer. It's like 4 times smaller than the surface mount Arduino chip you used for your accelerometer. So you can see that this is not that easy to solder as well, but it's doable. And this is very difficult. And I think after finish this project, you'll learn a lot. For example, if you only have one 0.7 LiPo battery cell to power up the 0.3 volts device, what are the regulators you can use? What are these regulators you can use? You know, the one we have, for example, the 3.3 volts. Remember the 3.3 volts regulator you have used for the power supply module? I think that was maybe this one, this guy. The dropout voltage for this guy is like 1.2 volts. If you have 3.7 volts, it's going to be dropped to like 2.5. I will not be able to turn on that 3.3 volts device. That's the problem. I have to find a very advanced one or high dollar one. Okay? And I use this really low cost and regular one. That's why I have to go to TI's website and do the search and filtering for a while. Eventually find out this one. Definitely there won't be any. I think that's this guy. Yeah, you won't be able to find any libraries online. You have to make the footprint and schematic, the symbol by yourself. And these are the connections to make it work. And that's the ESP32's microcontroller, all the things required to run it. And you don't need the oscillator because everything is inside the box. You just need to power it up and ground it. And this is the accelerometer to measure the angle, and gyroscope in there as well. And this is the PCB design. I think part 2 is optional. So let's look at part 1. So this project came from a company called Mission Groups, and they take care of the horses, their health of the horses. So one critical thing for the horse health is they couldn't visualize the injury of their legs until too late. So the changes are just so tiny they couldn't visualize. But they're still riding their horses and running their horses. But in the future, is causing really serious injury, and it's going to be a lot of issue with that. So they used to use a laser detector and shooting laser from the 2 sides in order to find out the minor changes of their legs. I don't know how that works, but it's usually costs more than $100,000 for that equipment. And also, you cannot let the horse or have equipment can follow the horse when the horse is running or walking. It's pretty much like static. The equipment are sitting there and let the horse just walking back and forth through the lasers. So they want to embed a some motion sensors into the horse legs or wrap it to the horse legs. But sometimes it's getting difficult because if you use the angle or speed sensors on horse legs and can measure if it's equal or even on the two sides, but it cannot measure the ankle. You wrap up the sensor to the leg, probably it is able to measure the injury of the knees, but the ankle is difficult. You cannot put a sensor over there. So this idea is like if you can put a sensor embed a sensor into the horse shoes in order to measure the movement of the angle of the ankle, for example, the speed, the acceleration of that joint. So my job, this was just the phase one. That's kind of like a small project. I was joking about that. It's $25,000 grant and it's worth a Camry. But this is just a very simple device. That's why RD is expensive. Right? If you want someone to develop a embedded system somewhere, like making a product like that, worth a car. So the phase one project is just to get the data from the horseshoe and send it out to a data center and log it to the SD cards. The logical next step is to look at the differences of the signal collected by these sensors and SD cards and compare them. So what are the signal processing techniques you can use, like machine learning? You can see there's anomaly detection, any bad waves that it can detect. But that's kind of like phase two's idea. I think the guy is still trying to acquire funding for phase two. I don't know when it's going to happen, but this was done. The phase one is done. And what we are trying to do here is embed a 3.7. I'll put it here so you can look at the monitor. I'm getting this recorded. People can see it. So the battery is a 3.7, just one cell level battery. Okay. And this is definitely not the smallest, but there's a trade-off in between the size and the power. So this one is doable, is okay. It's not the biggest, not the smallest, but it works. And put a battery here, and because if you mount it to the horse hoof, you won't be able to take it out and recharge it very often. So you have to make it rechargeable. And battery is here, and we have to put a charging circuit just next to this battery. And the charging circuit is the one the PCB designed in the midterm exam. So that's a charging circuit. Right. So you can charge it up, but at the same time, it's supplying a 3.7 volts to this board. And remember, I have a regulator on the board, so it's actually being stabilized to 3.3 volts to power up this EPS32 chip. I didn't seal this metal cover of the chip because I think this is a kind of like heat sink. If I cover it, I don't know where to dissipate the heat. It can be a problem for the board. Okay, and it's going to be totally wireless communication because there's no way that you wire it up to somewhere when the horse is walking or running. Right? It has to be wireless. And if you want to send it wirelessly to something like this to log the data, could you use Bluetooth? Yeah, it is Bluetooth actually. Yeah. What about Wi-Fi? Difficult, right? Yeah. LoRa is a low speed and long distance. So for example, someone just want to collect the data on their iPad when they are looking at the iPad and trying to log the data when the horse is running away. So the LoRa communication actually can transmit signal within like 10 kilometers range, somewhere around 6 miles. You can still receive data. But remember, the trade-off of that is If it's long distance, then the speed is low. If you are sending real-time signals and being plotted, the real-time angle signals or gyroscope signals is angular speed signals. LoRa probably is too slow to do that. But if you are sending out temperature or humidity data from the field, it's probably LoRa is a pretty good choice. Right? Just the one data point each time. The temperature is not changing that fast. Doesn't like this one. It's just a real-time plot. Have to capture every single motion of the hoof in order to figure out the laminas of the legs. Okay, so quite a few of these available technologies are not really the best choice. So Bluetooth probably is the best for this case. But what's the problem with Bluetooth in general? So we connect our phones to the car. We can even play music over Bluetooth. So the speed is okay, pretty decent. So no problem with sending and receiving the data. But what is the issue for Bluetooth? The range, right? Sometimes you play it downstairs, and if you are outside in the living room, it's okay. If you get into the restroom, it's getting disconnected sometimes, downstairs, upstairs in the room. So Bluetooth is not able to have a limitation of the ranges. So then how do we log the data to here? Another question: why don't we log data here directly? Yeah, it's on the phone. Yeah, you cannot take it out, right? So that's the problem. You want to do a test and analyze it pretty often, right? So nothing can be taken out from after you seal it. So it has to be sent out, and has to be sent out wirelessly. So that's the constraint of the project. So how to do that? Definitely, this guy is able to receive it from here. So just wrap this to the back of the horse, right? Okay, so it's always with a data center. So this is called a data center, and I only have two here. Probably one mounted to this one, mounted to the front right, and the other one mounted to the front left. So this data center can receive data from these two shoes. And if you need more, you can do up to four over here. Okay? And it's pretty convenient to use ESP32 because ESP32 has a really decent evaluation board that I can directly play with instead of making a PCB by ourselves at the very beginning. So it directly has USB to program, and the PCB here has a antenna. So you can use the antenna directly communicate with the board here. When you are designing the board, you don't have to draw the antenna yourself. That's the tricky part. You don't want to do that. So this chip, we have a lot of these chips. It's not really a chip, it's just a module, because underneath the cover, it has a CPU, has the oscillator, has all the peripherals in there. They don't want you to customize it, you can tell. That's why they put it in the cover. The good thing is, if you design the PCB with a footprint for this ESP32 module, then you just power it up and ground it and connect all the like I2Cs to your circuit board, and you can make a PCB, customize the PCB with the ESP32 really quickly. And it's going to be a wireless module that I can use for a lot of other applications, not just transmitting the accelerometer's data, but also control a little two-wheel robot, the one we are going to use in the fall semester, the two-wheel balancing robot. We are going to use this one as well to control that, use a joystick. So this is a really good sensor to use and to run. So usually the connection between the board and the SD card is SPI. If you look at the pins here, the SPI has certain connections. So it's basically MOSI, MSO, and clock, and enable pin. So 4 pins for the SPI vertical. And again, in this class, we are not programming the fundamental logic of SPI. This is something being covered in CE433, but not here. You make the connection, use the library, it's going to work. Okay, you'll be able to write data to here in text files or DAT files, and you can open it up using or plot it using Python later on, right? And the student who worked on this made a 3D printed cover or container and put a battery cartridge over here. So you can use battery to power it up. These guys. Is this easy to recharge it, the battery? So what we did is we have another box similar to this one, and we use a battery cartridge, like these battery cells, and connect them to a wrap, kind of wrap it around the lag whenever you have to charge it, recharge it, okay? And then use a cable to connect to this jack header and turn it on. I think it still has power in there. It's been like 3 years, okay? So there's no problem to recharge it. I know it's not really convenient, but usually when you are charging it up, the horse is not running around, just standing there waiting for like 30 minutes. You can fully charge the battery, right? And definitely this won't be as durable as original shoes, okay? But this is not being used for all the time, I believe. Maybe just for the horses, looks like they got some laminates on their legs, then takes a week, probably the entire week to do the testings each day. But definitely this is not for healthy horses, I think. So it's okay to cut a hole here and seal it using a different material, and also here. And I believe this will be broken over the time, but as long as it's able to stay there for a week or so, it should be fine, I think. And now let's look at the code or schematic. So first, install the libraries to your Arduino IDE. This is pretty straightforward. Problem here. And just keep in mind that when you are programming this ESP32, we have to keep holding this push button, push it down in order to enable the programming function of it. And when you start a new project like this, it's usually just taking baby steps each time. You cannot just build everything and trying to verify the functionality of it. So the first test I did was the ESP32 communication with a sensor. Right? You want to see if you can receive data from this accelerometer module. There's nothing about wireless. It's just a microcontroller receiving acceleration data into the chip. And so it's the I2C protocol. You can see it's ICL, SDA, so it's the I2C. And I2C have to use 10K pull-up resistors for I2Cs. That's why I use these two 10K resistors. It's a very simple connection on the board. And I think you can make the connection in like 2 to 3 minutes. And if you run the code here, you're going to receive data in your serial monitor in like 10 minutes. Very simple first task. And if you look at the code, so the I2C device, most of the time they have an address of it. So it's hex number 6A. That's the address of the I2C device, which is the accelerometer. I highly recommend that you open up so this is that link. I'm going to fix it after this lecture. So I highly recommend that you find the MPU6050, which is the name of the accelerometer board. Find the data sheet of it, and there's a table, have all the addresses and the the registers in there, and you have to use this data in order to program it. And that's AX, AY, AZ, the three axes of the acceleration, XYZ. You have to keep in mind that you must reset your accelerometer every time, otherwise you are getting an error. So here's a place, I believe, here's a place to reset it. So it's 6B. I have to put a 0 in there first in the setup function. Okay. And then you can get started. So that's the starting register. I think that's the acceleration data's starting address. And this is something can be confusing. You probably haven't done that in the past. So the data stored in these registers are, you can tell it's 3B, it's just 2 hex digits, which means it's a 1 byte, right? But this the accelerometer chip stores the acceleration data in the 16-bit style. So which means you need 2 bytes to store that data, right? That's why you have to read it first and shift it to the left by 8 bits, and then OR it with the second one with the next byte. How that works is, so for example, this is x axis acceleration, is one direction's acceleration, and that's the MSB. This is a LSB, or this is a higher byte. This is a lower byte. Each one has 8 bits in there. For X, you have 16-bit of data being stored in the accelerometer, and it's the same for the Y-axis as well, and same for the Z. Right, and each one has 1 byte in there. And you know that this is a higher 8-bit. All right, this is a lower one. So how do you make it up after you received all the data in there? You have to combine them together to get the actual number, right? Otherwise, these are just like 1 and zeros. Actually, the 1 here, if you get an LSB in this byte, the 1 here is actually the 9th bit of the data. You know what I mean? So the real data, if you want to make up the real data here, you have to combine these 2 bytes together. So put the MX here and LX here to form a 16-bit data. So the 1, this guy, is actually bit 9. It's not 1, it's like 2 to the 8th. Does that make sense? You don't have to worry about like why or how the accelerometer does this. When you open the data sheet, you can find that the x-axis, acceleration data of the x-axis, is a 16-bit data, but they are being stored in 2 bytes in 2 places. And they tell you that this, the top one, is a higher 8-bit, and the lower one is a lower 8-bit. So I have to combine them together to make up a 16-bit data for the x-axis acceleration. So how to make in programming? So every time you read it, it's only reading 1 byte or 8 bits. After you receive it, so the first one, which is starting from address 3B, you shift it to the left by 8 bits. So it used to be here, right? Used to be here. You shift it to the left by 8 bits, so now it's here. And you are making this 1 to be 2 to the 8th instead of just the 1. So it becomes this thing with all the zeros, like 8 zeros, because you shifted this byte to the left by 8 bits, right? So, and you leave all these locations to be zeros. And the second time you read it again, which is gonna read, because you can see this function is a request from this MPU, this address of the accelerometer module, and this number is 6 bytes. So you want to start reading from this address and keep moving for 6 bytes, because 1, 2, 3, 4, 5, 6. You're getting 6. So 2 bytes for each axis. You know what I mean? And you can put a 4 here. If you put a 4 here, then when you do the where.read function, it won't read the z axis anymore. It's going to just read 4 bytes. You're going to stop at the lower byte of the y-axis. So I have to put 6 here in order to read all the bytes from the 3 axis. Right? So this is what that means in this function. And now I start reading. The first byte, but you move it to the left by 8 bits, and then you OR it with the next read. So the next read is going to have the byte over here, right? Anything, it can be 1, can be 0, doesn't matter. It depends on the data. And you OR it with a 0 here. Definitely this one only has data in the lower 8 bits. So all the other ones are just zeros. Okay? So if you OR it, you actually combine this one and this one into one 16-bit data to form one data in the memory. It can be x-axis if you do it. OR it once, you are making a 16-bit acceleration data for x. If you do it one more time, you got a y. If you do it one more time, it's going to be z. And because you have this function before doing the where.read, so that's why every time you put a where.read function, it's going to read the next. It's going to read the next byte, starting from this this byte. That's the starting address for the first byte of the x-axis. One quick question. This address, is it the higher byte of the x-axis or lower byte of the x-axis? This one. As a starting address, right? You want to start from there. It's on the very top, and then the next is going to be something else. But is this 3B 0x 3B? Is this starting address of the higher byte or lower byte of which axis? That's right. See if I have a data sheet over here for you to look at. I have a snapshot of that one. Remember what's the address? 0x what? 3B. 3B, right? 3B, yeah, so here's the data sheet. The data sheet has 52 pages for that simple chip. That's I2C protocols, you don't have to worry about it. Oh, so data sheet and the register is a different thing. Register map. It's making things complicated. See, register map and product specification. There are different data sheets. Glad this is recorded so you'll know what's going on. Okay, that's a register map. Right. These are the addresses. Definitely hex numbers. And here it goes. 3B, right? It's X out high. So it's acceleration data, X output, high byte. It's bit 15 to bit 8 as a higher byte. And then next just follows this one. It's same thing, but lower byte. That's bit from 7 to bit 0. Okay, so I have to combine these two in order to make a 16-bit acceleration data for the x-axis. And the next is y, right? Y high, y low, z high, z low. And followed by temperature. If you put an 8 in your code, you are able to get the temperature data out of it as well. Why do you need a temperature data? That's interesting. I think sometimes they need a temperature data to calibrate the sensor for some reason, but I don't think we are doing that for here. Okay, so we got a temperature, gyroscope, the angular speed required for a lot of situations. Same thing, x high, x low, y high, y low, z high, z low. And they have data for a lot of other things we don't really use for this project. You can refer to it later. But definitely keep in mind that there are two different data sheets. The first one is specifications, and the second one is a register map. I just Googled it. You just Google the same way I did. You should be able to find it. It's better, like, probably I'll just get a link on the website later. So this is the data sheet for the specifications. This is also very useful because when if part 2 is optional, then you don't have to design the PCB out of it. But if you are designing a PCB, you need to know what are these connections required to make this sensor work. I think this is just a diagram. This is not a schematic. I have to find a schematic online. That's what I did, I think. I have to find a schematic of the module because they are using the module and the module works. And you just need to duplicate the circuit on the module to your customized PCB. Okay, and if you use this code, you should be able to see the X, Y, Z accelerations. I was shaking that board. That's why you are seeing these waves. If that's how you can verify it. Okay. And so once you get the data, you have to convert it into the how many G's actually. How many G? Because that's the acceleration. The unit for the acceleration is just a G. How many G's, right? And you can change the sensitivity of it. There are several options. If you put a 0 for that bit in the register, in the certain register, so where is that register? AFS SEL. Let's see. Where is that? That's a configuration byte. Okay, it's this guy. So where is this guy? This is 2 bits. You see, it's bit 4 and bit 3 of this byte. So if you want to do a configuration, you should do a write operation to this address, to the I2C communication first. You have to write it first. Write something to this configuration register. Write a 2-bit, configuration code into it. 0, 1, 2, 3. Why? 0, 1, 2, 3. Why there are only 4 options? Or let's say that. Why 2 bits here? Why is 2 bits for this one? For this configuration? It's just the configuration in the byte, right? If you turn it on, you turn on some functionality. It's like a switch. You don't need to know the details of how the digital circuits were designed. We're not doing that, right? It's just the microcontroller level programming. So it's right now it's the register level configuration instead of just the C++ programming. Why 2 bits? Yeah, there are just 4 possibilities over here. So you just need the 2 bits to figure that out, right? You have 4 different ranges: 2G, 4G, 8G, 16G, and I think for most of the time we use this one. Okay, so in your data you have to convert this data into how many Gs, because when you are receiving the data or converting the data from the register, these are not with a unit of how many Gs. You could imagine that like this is a 16-bit battery number, and if you got like 100 in there, you're getting 100 G. I don't think it's possible, right? So these are just LSBs. So whatever the data being stored here is a unit. The unit here is just how many LSBs, which makes sense because one LSB is just a 1, right? If you got 100 here, it's just 100 of 1s. So the unit here is just how many LSBs for the 16-bit data. And because you chose, for example, a 1, like 0, 1 for this guy, and you know that it's 8,192 LSBs per G, you can convert. You can use your the 16-bit data divide by this number, and you are getting how many Gs. Make sense? Okay. And just keep in mind that if you're using EPS32, you have to put a dot point, like 0.0 here instead of an integer in order to get a floating point data. Otherwise, it's just outputting a very weird, like something like this, just on off instead of all the details of the data. I don't think I have any really specific tasks for you guys to design a specific code for any of the tasks. It's generally just repeating what I've already done here. Let's see. SD card, explanation of SPI, and so this module is available in the drawers, one of the drawers as well, and also as the IC cards as well. And this is a 5 volts device. So, but your ESP32 is a 3.3 volts. But you have to use 5 volts to power up the IC card. And however, the IC card adapter, this guy, has a 3.3 volts regulator. See? Did you kind of see that? 3.3? Yeah, so it kind of works. You can still do it. But I have to power it up using 5 volts. You know what I mean? Yes, the SD card also has a power supply. It's a solid state device, right? So VDD and ground. But that SD card itself, as a storage chip, it receives 3-point servos from its power supply. But it cannot power up this module with 3-point servos because this device has like somewhere around 1 volt of low power voltage. So I have to power it up using 5 volts. The VDD VCC here should be 5 volts. Keep in mind. So where can we get the 5 volts? Is this just a really power consuming device? It's really not. It's not. So you can use the 5 volts from either from your power PCB module you developed in the beginning of the semester, or you can use the 5 volts from the Arduino board output, or anywhere. It's a low power device. It's okay. Make the connection. Again, you want to start with very simple things. Instead of putting everything together all at the same time, it's better to just write a constant to the SD card so you can verify if the communication between the SPI communication is working correctly. So at the very beginning, don't try to receive like acceleration data and then send it to the SD card. Just throw some constants like 1 zeros. See if you can do it. Okay, and then move to the next, which is use this one, receive acceleration data, but not wirelessly. Just keep in mind, adding 1 variable each time when you are designing embedded system. So put an accelerometer in there and use this guy to receive acceleration data through the I2C and send it to this SD card using SPI. Okay, see if you can store acceleration data to the card. And these are the data, and you can actually tell they are being separated by commas, right? As the TXT file being stored onto the card, and you can open it up in your computer. And then adding wireless communication to it. So start with acceleration data and wireless communication. The receiver receives the acceleration data, and you use a USB cable to show it in the monitor here. Okay, it's just adding more to it. And I believe the last one is you just put everything together. Right, so this guy sends the acceleration data and send it to here wirelessly, and this guy logged it to the SD card. So that's the entire system. That's it, right? 1 sender, 1 receiver, and SD card as the data storage. And this is the XYZ acceleration being stored on the SD card. I'm gonna, try to write up a Python code script to plot it. Right? Y-axis over here is up here. Like that. It depends on the way you hold it, or depends on the way you plug it into the board, right? If you rotate it by 90 degrees, you keep the y-axis vertical or perpendicular to the ground. Then the y-axis get a 1g acceleration. You know what I mean? Because it's 1g. If I keep x perpendicular to the ground, then x get a 1g, but all the other two are nothing. It's flat. Right? Any questions on this? Yes, common ground for everyone. Yeah. Oh, the receiver. That's right. No. But if you want to power them up using 1 power supply, then you need it. I think. Yeah, it's better to have a common ground. But sometimes for the wireless communication, you don't, because these two, they don't have a common ground. Yeah. But if you use 1 power supply for all of them at the same time, you do need a common ground, because they can see that the same 5 volts instead of different levels. They're all relative. If you have common ground, they know that's exactly 5 volts on each side. Right?